All right. So while we give everybody a chance to connect in, and hopefully we haven't lost too many strays over on the old Zoom link, that's why we sent a excessive amount of reminders. So hopefully that wasn't too much. We've got a little splash screen up today, just something that was suggested by one of the other CARC tracks that we quite liked. Just something to look at beyond staring at my poor face and how I'm keeping myself while I'm in quarantine at home, you know, like the rest of us. But the usual things, please keep yourself muted unless you have questions. We already talked with Doug, who's going to be our presenter today. He would like us to interrupt whenever we have questions throughout the meeting. Feel free to do that with audio, or feel free to throw that out into chat. Troy and I will help monitor the chat as well as anybody else can, and raise those questions that show up in chat to Doug's attention, as I don't think it's easy for the presenters themselves to see the chat when they're working on their own slides. Troy and I guess would make the quick plug. You know, we're planning future months meetings. If you have any suggestions, ideas, especially while you're maybe looking for something to diversify your work model that we're all in right now, feel free to raise your hand, you know, whether you're willing to present on something you're doing or just interested in helping us put something together that you're interested in hearing more about that somebody else might present on. Feel free to, you know, reach out to this. Troy has already shared the Google Doc link. I'll paste it again in a little bit. Please join us on the Google Doc, sign in, and help us keep notes. Keep track of questions, answers that are given. There's also a spot on there to go ahead and plug in some future topics. We are recording again today. We will post the recording up onto YouTube after we're done. And we do have Doug's slides linked into the Google Doc so that people can get to later as they have interest. So with that, I'm going to stop sharing my screen and kind of turn things over to Doug. And we will go to just before the turn of the hour and go from there. So let me, I've got Doug, you're on mute as well. I put you on that if you didn't know, but let me go ahead and stop sharing my screen.
All right, can everybody hear me okay?
Yep.
Good. And let's see, I think everybody should see the slides in presentation mode now. So I'm Doug Johnson, and the topic of the talk today is direct-to-the-chip warm water cooling HPC systems at OSC. So first, I want to thank Brian and Troy for the invitation to give this talk, and for everyone in attendance, thanks for your time. I've got a disclaimer before I get into this talk. This is pretty informal, and like Brian mentioned, feel free to jump in at any point. You know, the level of informality for the talk, there's no paper associated with this, so this is just in our experiences with our latest system. There probably should be a paper that comes out of this, maybe sometime in the future. I also want to mention that I'm, you know, not a pro at the facilities stuff, so there's probably people in the audience that are much more experienced than I am, and I welcome people to speak up if I've got any misrepresentations, gross misrepresentations. I'm sure I've got plenty of small ones. There's some additional material at the end of the slides for pointers to documentations for the people who really are the pros at this. With that, what's the background? So, you know, liquid cooling for computers is not new. In fact, it used to be kind of required for the larger systems, so the old school big iron systems. And then, of course, we've seen plenty of examples of the new school big iron systems. Most of us are not buying computers like this. We don't have budgets of tens of millions of dollars, and you're building multi-megawatt systems. We've also seen lots of attempts at experimental or exotic systems, you know, things doing interesting things with it, you know, phase transition, you know, to cool chips, and that's more experimental. What we're going to be talking today are things more in the commodity realm, and for our community, for the campus community or the regional supercomputer centers, liquid cooling is going to become more of a thing. So let me give some data to back up that assertion. So we've seen an increase in the physical packaging of servers and the lifetime of our Beowulf cluster projects. We used to use pedestal computers or 2U servers when we were building these commodity clusters, and those have shrunk down to the pizza boxes, the 1U servers, and now we're kind of all at the half-width 1U form factor. So we've seen this at least 4x increase in server density. And a lot of this packaging improvement is not driven by us. It's not a small market for HPC, but the people really driving this are the cloud and web scale deployments. So we're kind of beneficiaries of that larger market. And at the same time, these systems are becoming more densely packaged. The components that go into them are just getting hotter and hotter. So the top bin parts from Intel these days go out to 400 watts per processor. And then throwing GPUs into the mix, that's going to be another 70 to 300 watts per accelerator, depending on what you're putting into the system. So the bottom line is that it's, unless you're partially populating racks, you're going to be well above 30 kW pretty easily. So the reason the 30 kW number is interesting is because even if you have the best data center for air cooling, that's where you're going to start to run into challenges with exclusively air cooling systems. Now that I'm not going to go too deep into that. So that's kind of a broad statement. I'll give the disclaimer. And we've seen examples of racks that are even more absurdly dense than that 35 or 40 kW rack. So 200 kW or racks are in existence today using commodity Intel processors. So that's a remarkable amount of power density. So like I said, with that amount of power to a single rack, air cooling is just not feasible for many configurations. So direct to the chip liquid cooling is a solution, and warm water direct to the chip may be a possibility for many. So I'll come back to that a little bit later, but on to the other things driving us down this path. Processors have variable clock rates, and the clock rates are dependent on how many cores are in use and what kind of power distribution you have. Do you have enough power delivery in the system to sustain all the cores running at a certain clock speed? And most of our HPC packaging is going to have sufficient power, but another variable that sets the clock speed is going to be the temperature. So what is the ambient temperature of the processors? So, these variable clock speed processors with their turbo states that are higher than the nominal clock speed, we want to take advantage of that. But we need steady temperatures for steady clock speeds. And if we don't have that, especially for parallel jobs, we can run into problems. So Amdahl's law, if we have one node that's running hotter than the others, even if it's not being throttled and it's running at its nominal clock speed, other nodes may be sitting around waiting for that slow node to finish. And then I'm certain that everybody who's run HPC centers is in the past few years been getting more support requests asking why runtimes aren't consistent when they're benchmarking the system. And the external state of the system, the temperature, and what's running on the adjacent nodes affects the performance of those jobs. So, we're being pushed down this path. And now that I've established the path that we're being pushed down, I want to take a few minutes to go into a review of power and cooling. Now, many of you know these concepts better than me, so others might be okay with it, a little bit of a refresher. So I'll go through these relatively quick. So first things first, given a spherical computer, where does the energy consumed by a computer actually go? Well, the bulk of it is internal resistance. So all the components are going to have this internal resistance that results in dissipation of the heat to the surrounding air or other materials. Mechanical work, that's actually a non-trivial fraction of the total power. And we'll come back to that more later because it's actually relevant for this warm water direct to the chip discussion. And then a vanishingly small amount of the power actually goes to real computation. So, Landauer's principles as the lower theoretical limit, something on the order of Planck's constant times some multiplier for each operation. And, you can throw rotten fruit at vegetables if I'm getting that really wrong. I haven't read the paper in a long time. So that internal resistance is the dominant thing. And we have to have a place for that energy transfer. We have to have a place for that heat to go. So most of the time that's going to be dissipated through conduction to air. And that's the air in the room. And, we're consuming energy, joules, and the rate at which we consume it is joules per second. So watts, like I said, most of it is that internal resistance. A small amount is the fans, and that's moving air, doing mechanical work. The rest of it has got to be moved through that conduction to air or other mediums. So that brings us to the data center. So we've got the ambient air, we've got chilled water systems, we've got the computer room air conditioners or air handlers to move that air around. And they're either going to dry coolers or cooling towers. Those are where the refrigeration cycles are running to help move that energy from medium to medium. And warm water systems, and that fits into the whole equation here. And that's where we would leverage that condenser water loop and the cooling towers outside and bypass some of the refrigeration condenser units. So where does the money go? The bulk of it is obviously to power the IT equipment, at least if you're doing it semi-efficiently. I'll come back to that in a moment. But the next biggest thing is probably the refrigeration cycles, so those condensers. And we've got the universal sign of $4. So that means you better call for a reservation and bring a jacket. Fans are probably the next above pumps that are moving water if you have water or refrigerant being pumped. And as a refresher, the power utilization efficiency is a ratio of the total power being consumed for the data center divided by how much is actually going to the IT equipment. Ideal is 1. That means that nothing is being wasted at all. And there are some people that are getting vanishingly close to that 1. NREL has a data center that is extremely efficient. There's some other experimental ones that do an extremely good job. 2 to 3 is not uncommon. So that means that there are a lot of people out there that are putting more power into their data centers in the building and then the IT equipment. And then for that refrigeration cycle, a key ratio that we're interested in is the coefficient of performance. So that's the heat removed divided by the power required to run it. So this is where sometimes it's easy to forget that if your air conditioner is moving a kilowatt of heat per hour out of the room, a very small air conditioner, it doesn't take a kilowatt to run that air conditioner. So, we get these magic things to happen with the refrigeration cycles where the power required to run that cycle is actually less than the heat that's being, or the energy that's being transferred. So the typical coefficient of performance is 2 to 3. So this is why that refrigeration cycle is that $4 designated kind of unit. It is power intensive to have those condensers running. So I want to take a pause for a second, make sure that I'm not missing somebody flagging me down for a question or anything. Any questions or comments?
The only question I guess I'd ask is, with what you were just saying about PUE, when you're looking at your facilities before you're playing with liquid, did you have a number for your facilities before?
Unfortunately, no. So let me explain why. So we're in a shared data center, the State of Ohio Computer Center. It's a Tier 4 data center here in Columbus, Ohio, and we share it with state agencies and other universities. It doesn't have some of the systems monitoring that we would have needed to fully have quantified our complete power picture before we started introducing this hardware. So we're kind of missing some key variables to be able to answer that question. And along with that, let me explain some of the constraints that we're working with. So like I mentioned, the center is not designed for high density HPC. We're just one of many tenants in the data center. And so there are others like Department of Taxation, Public Safety, and other agencies that take much higher precedence above us. So we don't have we're not the only tenants, and while the building engineers have accommodated us well, we haven't done everything that we would like to do. Another constraint that we work with is that we have limited chilled water in the data center, and actually it's not plumbed to our suite. So even if it was, the chiller units are just not large enough. So what we do have a good supply of is the condenser water loop. This is the water for the crack units, and that is tied in with some large cooling towers outside of the data center. And that cooling loop meets what's called the ASHRAE class W3 for liquid cooling guidelines. So the bottom line is that we're under 89 degrees Fahrenheit for our water temperature. And that is kind of a good ingredient to have for a lot of warm water cooling solutions. Another thing that's different about our data center from a lot of other academic supercomputer centers is that we pay rent and power through our operating budget. I know that this is not universally true, so I don't want to come up with a an estimate of whether we're in the minority or the majority, but a lot of academics HPC centers that bill doesn't exist. And at the same time, when we make improvements to the data center suite, we need to pay that out of our own budget, whether it's operating or capital. So any cooling or power and power distribution improvements, we need to pay for the full projects. So that brings us to what we started to encounter when we worked on the Pitzer HPC cluster project. So this is kind of a glamour shot of the system. I'm putting the end product first, but you know, got to have some nice graphics in the presentation. So the Pitzer HPC cluster is named after Russ Pitzer. He is a professor of chemistry at OSU, and he was instrumental in founding OSU as well as ORNET, the Ohio Academic Research Network. And he made fundamental contributions to computational chemistry. So we were really happy to be able to honor his contributions with naming the system after him. We did a request for information for the overall system back in 2017. And in the RFI, we gave basically 3 different options for how the system would be cooled. Either we would partially populate racks to stay below thresholds for what could easily be air-cooled with existing infrastructure. The second option would be for denser racks, but with some kinds of augmentation to support the higher density. And then the third option would be some sort of liquid cooling solution, including warm water, specifically including warm water is what we preferred. So a number of vendors proposed warm water solutions that were direct to the chip. Ultimately, we selected Dell and CoolIT as the vendor, and we've been in production since about November of 2018. We've also decided to expand the system, and that also includes an expansion of the warm water cooling hardware that we included in the original purchase. And we expect to have delivery of that in June of 2020, though it's been delayed, and we could possibly see more delays due to, well, you know, what's going on in the world. So our goal is to be in production with those systems by September 2020. So the original Pitzer cluster is in the left column, and we had some standard compute nodes, 224 of them, dual GPU compute nodes, 32 nodes, and 64 NVIDIA V100s total. And also some large memory compute nodes and the interactive login nodes. Of those systems, we have direct to the chip cooling for the processors in the standard compute nodes, as well as the dual GPU compute nodes. Now that's for the CPUs only. We do not have direct to the chip cooling for the GPUs. That is not and was not an option, and I'll come back to that more in the conclusions. So there's a non-trivial amount of hardware in the Pitzer system overall that does not have the direct to the chip cooling.
So can I interrupt a question?
Yeah.
So with what you just said there, because this is something, I guess, in our interactions with the vendors, we've heard some similar statements, you know, and you're going to sound like go into deeper, so I don't want to go there yet. But this idea that in some cases you're limited on what actually can be liquid cooled. What we have been purchasing ourselves is not the highest end of the CPUs. You know, we have found our own sweet spot. But with the way you're describing it, it's just kind of adding something to my mind right now that I haven't been thinking about before, which is, if I'm going to do that, does that now all of a sudden incentivize me to go and buy the best of the best because I'm going to potentially pay a little extra for this infrastructure? Why not make the most of it that I can? kind of, was that part of your decision, or were you guys already buying kind of higher end, or were you midfield? Because we're gold CPUs, we're not in the platinum region.
Yeah, you can see that in the original Pitzer, we were gold as well. We were able to, through, a competitive process, get some, good competition is good. AMD has some good offerings out there, and we were able to get platinum processors, kind of the top end part for our expansion. But I don't think that the bin of the CPU really factored into it for us, because we always knew that we were going to be into the roughly 155 watt part. We know that there are deployments out there where their workload can use fewer cores, or different clock speeds, and they can tailor the purchase to kind of optimize the price performance or the watt performance kind of ratios. Since we're building a general purpose system, we have to buy the least bad processor. There's no such thing as the best. And to kind of directly answer your question, the extra infrastructure, overall, including installation, it's only about 3 to 5% of the overall purchase price is probably the round budget numbers to use as estimates to keep in mind. And so if you're, looking at having to put in extra crack units or extra air handlers, or already having to go with rear door heat exchangers, there might be, just on a sheer dollar basis, an advantage to going with the direct to the chip cooling.
Can I just ask, I'm sorry if I missed this, what is the form factor of these new nodes that you're adding?
So these are the 1U half width chassis. So 2U chassis with 4 1U half width servers.
Is that the F series?
I think they're called the C6420s.
C6420s.
That's for the standard compute nodes. The dual GPU compute nodes, those are in, I believe those are in Dell R740s, which are 2U systems. Right. So they're fairly large.
Okay, thank you.
The newer systems where we have the quad GPU nodes, those are 1U. So those are quite dense. But then again, these are not direct to the chip cooled. There's no liquid cooling options for these going forward at this time. So I guess it's fortunate we have so few of those. We'd like to have more, but our budget doesn't, and a budget doesn't accommodate it, and it would make the facilities part of the project harder.
So then maybe a follow-on question for both the existing generation as well as your expansion. Do you know what your, ignoring liquid and air for the moment, do you know what your kilowatts is per rack? And then yes. The follow-on question is, do you know what then your divide between liquid and air is between those two?
Well, I don't want to give away the main slide, but the densest racks for the Pitzer cluster are 30 kW. And I'll come back to just how much heat are we extracting using the warm water direct to the chip cooling.
Great. Thanks.
Fortunately, it's not far away. So this is the non-glamour shot with special lighting of the Pitzer cluster. You see the 7 racks total. The 4 closest Dell EMC racks that you see, those are the dense racks with 60 dual processor servers, 15 of those 4 system chassis in each rack. The cabinet that you see in the foreground is the CoolIT CHX650, the coolant distribution unit. This is the heat transfer unit between that external condenser water loop and then the internal secondary loop that goes to direct to the chips. So just to set the stage and become more focused on why warm water cooling. Our data center didn't have the appropriate layout for high density systems, whether having chilled water or deeper plenums, and be more suited for high density air cooled systems. The direct to the chip allows for higher density and more efficient floor space use. So we didn't have to limit how many systems we put in each rack. There's efficiencies because there's no refrigeration cycle for a significant fraction of the cooling for the systems. And like I mentioned earlier, fan speeds do factor into this. So if you are removing the heat directly at the chip, the chassis fans to move that cool air from the cold aisle, they are not running as fast. And I'll come back with a demonstration of that a little bit later in the talk. And then it removes load from the crack units or the air handlers. So that could also allow us to lower fan speeds in those units for further power savings above and beyond shifting load away from the refrigeration cycles. And then because you're removing the heat directly at the processor, it opens up the option of setting your temperature higher in the data center. And that will, at the same time, you can preserve the consistent performance. So right now, I'm certain people are looking at ways they could save money on air conditioning by using the wider operating ranges that servers and other IT equipment is rated at today. So we don't have to have the data centers set at meat locker temperatures anymore. The downside is that if you don't have some of those low temperatures, it might upset the consistency and performance, those turbo states that you're seeing with modern processors. So this is the left brain view. It's kind of a throwaway slide. It's a screenshot from a web interface into the system. The right brain view is this, of what the cooling system looks like. The leftmost picture is the underfloor supplies for the individual racks, as well as the coolant distribution unit, that heat exchanger that's the interface between the secondary loop and the external condenser water loop. That is plumbed into the manifolds in the individual racks, and you can see the hoses that go into each of those 1U half-width servers. So it does complicate the physical packaging of the racks and cable management a bit. So you will definitely want to go with as deep of a rack as your vendor supports, and you want to go with a wider rack. So a standard 24-inch rack is not a good idea when you have this type of hardware. And then in the rightmost, you see the ultimate interface, which is the CPU cold plate. That little unit where the hoses are running replaces the standard heat sink that's on the processor.
So before you jump off that slide,
yeah,
the middle picture, because the C series, I have air-cooled variants of them. Do you get feedback from your staff that servicing those blades, because you have to pull the blade from the backside?
Yeah.
So when you, obviously you're going to decouple the liquid tubes for that particular blade, but are all the cables above and below fighting them? Is this a love-hate, or are they good with it?
Well, it's a love-hate, but it's at a certain time in the process. So we are very engaged. All of our system staff are very engaged during the design step of the system deployment, and we drill home the message. Well, we can't do anything that impinges our ability to pull out a server. We don't want to have to shut down, big chunks of the rack just to work on one computer. And so I think in most cases, it's more of a minor annoyance than something that keeps the systems from being worked on. Most of the physical work is done by undergraduate student employees. And so I think that we've been successful in working with the vendors, and they've done a good job of the ultimate physical installation, where for the Pitzer deployment, we've had good experience in being able to physically work on the system. And I don't know if anybody else from my team, aside from Troy, is on the call, but if anybody is, if they have a different view, please speak up, or if you want to elaborate. But yeah, you will need to spend some extra time going back and forth with the vendor to make sure that the design is right, and the installers have to do a good job, or you will have problems. And so there's an advantage to this, because it forced us to spend more time thinking about this, because I will be forthright and honest. Our previous system, it didn't have this type of complexity with hoses, and we still did not do a very good job in avoiding some physical problems that make it hard to work on the system.
Have you had any problems with leakage?
We've had some initial challenges with the sanitary flange that was used for connecting that secondary loop to the CDU. So that was a more painful process to get it to be leak-free than what I would have ever anticipated, because it's the part that was being installed by the professionals, and it's large and not close to IT equipment. It was not so much a leak as kind of build up. This is a glycol mixture in the secondary loop, so you get something that looks like a greenish sludge. We've had one connector where we stopped using it for the time being, because when the hose is not connected, we were getting a bit of a drip. So what I think we did was we moved the hose and we put a temporary plug there. And we've got a procedure for cleaning it out, because that's what they think the problem is. But we other than that, it has not been an issue. And like I said, we've got undergraduate students working on these, and so we've had no problems with large scale leaks.
Thank you.
Okay, so what are the results? So like I said, this is an informal talk. So I've pulled plots directly from our monitoring system. So not the prettiest plots, but this is the data for the last year. And the power used by the system is measured using our HPC smart PDUs. So these are the networked PDUs where we can use SNMP to retrieve their instantaneous and counters for how many joules that have been consumed. And then the CoolIT CHX650, the CDU itself, is networked and has an SNMP interface as well. And you can get back a couple tens of metrics from the device as well. However, in the web interface, if I go back here, in the far right, we see that 59 kW box. That's the heat rejection from the warm water loop. So that's how much, that's the rate of energy being transferred from the warm water loop to that external condenser water loop. So they are calculating it and measuring it. Unfortunately, in SNMP, that value comes back as 0. And this is a cooling company, and the IT aspects of it, they're not as easy to work with as a typical IT company. And so that bug is still there even more than a year after we put it into service. So what I had to do was derive the value for the heat transfer. And the bottom line is we're achieving about 53% of the total power is going out through the warm water loop. And just to make sure everybody's aware, there's significant components in the cluster that are not part of that. So just to reinforce that includes the GPUs, all the power supplies, the Ethernet and InfiniBand switches, and the large memory nodes, and the login nodes are also air-cooled. So this total power consumed number is all of that hardware. It might be possible to work out what the power required is for the major air-cooled components, but we haven't done that yet. Just go ahead.
So we've asked the question and got, I think, the same answer you have, but I'm just curious if you got any more forward-looking feedback, or maybe you have a different appetite. But the fact that the GPUs were not an option, where you'd look at that and say that's a very dense, point of wattage in the machine, and maybe even some of the newer high-end network devices. From the vendor standpoint to you guys, are you seeing something on the horizon, even though it's not in your current expansion plans? What are your thoughts there?
It's more hope. So the reality is that the companies making the cold plates, they do have hardware for the GPUs today. It's just that the vendors consider it an aftermarket change that they won't support, and so it will not be covered under your warranty. However, there are white box vendors out there that will sell you a direct-to-the-chip warm water cooling solution that includes cold plates on the GPUs, and not even the MXM modules, just PCI. They retrofit the PCI cards, but it does void the vendor warranty. But the OEM, they say we'll do the warranty work, and so it is possible to get this. We're hoping that the larger OEMs will at some point have to offer it. Reality is going to hit at some point where they're going to be selling you racks with 5 or 6 servers in it, and that's it, because you just can't air cool it. So I wish I had a better answer, but that's kind of the boat we're all in.
Thank you.
So with direct-to-the-chip cooling, I mentioned that fan speed is lower for those systems, but I've committed the horrible sin of burying the lead. I mentioned earlier the importance of processor temperature to being able to achieve more consistent performance and stay in those turbo states or those higher burst clock speeds for longer periods of time. So I buried the lead on this slide. As you can see on the right, what we have are some temperatures from the Pitzer CPUs that are direct-to-the-chip cooled. And on the left are our previous generation of Intel processors, the Intel Broadwells that are air-cooled. So it's not really an apples-to-apples comparison, different generation of chips, but the bottom line is that the chips run much hotter in the air-cooled system, and the variability is higher. So not only is the temperature lower, that allows the system to run the fan speed at a lower rate, and that does have effects on the power. So you might ask, well, how much power really goes to fans? Well, I've got an answer. Now, this is a little bit of a quick and dirty test. So I'm not going to represent this as a complete study into how much power you're going to save by not running the fans as much if you have direct to the chip cooling. That would require more time. But the bottom line is that those fans, if you remember, they had those $2 signs for the universal sign of how much it costs. It's not as expensive, but if you do it every day, if you eat there every day, you're going to bust your budget. So here's what it looks like if we take the fan speeds from automatic control and temporarily force them to 100%. It results in better than a 10% spike in power. And I don't have the best quantitative presentation of the data here, but as you can see, we do typically see our fan speeds greater than 85% in the Owens cluster. These are in the C6320 chassis, the previous generation, versus less than 30% for the C6420 chassis in the Pitzer direct-to-the-chip warm water-cooled generation of system. So any questions about that slide before I move on to conclusions and any kind of discussion? So the project has been successful for us. More than half of the heat load from the system is rejected to that warm water loop. There's no refrigeration cycle. The pump to run that only takes a couple kW, so its efficiency level is quite high. The chassis fan speed is a further improvement for the overall power picture. So it's probably close to a 5% power reduction if you have servers that are continuously loaded like HPC centers experience. And this has been successful enough that we are continuing the model with our expansion of the cluster. So we are adding another CDU for capacity for the new systems that we'll be installing later this year. We still need to do some work to optimize how our crack units are used in the room, how many of them are needed, and to adjust the temperature set point in the room now that we have systems where that's less of a concern about causing performance or performance consistency problems. And then
so there is a question in chat. So Martin is curious about your temperature comparisons you did. So he's curious about it, like with the higher, newer AVX instruction sets. When those are used, the clock rates tend to go down, and they seem to be very thermally sensitive.
Yeah.
Did you do any testing with that perspective in mind?
We did some ad hoc monitoring with the turbostate program, but we don't have a quantitative kind of measure of what that looks like versus an air-cooled system. I think we have the data, it's just a matter of mining it. So when we asked the question about direct-to-the-chip cooling back in our 2017 RFI, one of the things that we were looking towards was whether we needed all of the space in our data center that we were paying for. And the success of this project has been good enough that it's, and our projections for what our systems will look like in the future as far as their density has allowed us to give up some of that floor space and reduce our operating budget for rent. But the bottom line is that it's not universally available. Not all vendors support it, and not all of their server lines have warm water direct to the chip options, and especially true for the GPU systems. So there's a big question as to whether that will be an option in the future. But like I mentioned, there's always the ability to go outside of warranty and do it yourself. So it depends on, risk profiles and risk versus reward. But we're hoping that this will become more widely deployed and that there will be more options in the future. So with that, I want to thank everybody. If you have any questions that you don't want to bring up here, feel free to contact me, and I'll just open up the floor.
So Alistair put a question in that's really similar to one I was going to ask. He's curious about, from the standpoint of product review, how painless is it to expand the cool IT? And that's kind of where I was going, is when you're looking to add more things on, is it full system outages? Not just one node, but new racks.
So here's something that I should probably mention. If you're doing a project like this, in that leftmost picture, make sure to install more ports than what you think you need. Or if you aren't sure how many you need, at least install some shutoff valves and a loop so that you can keep the circuit complete and do the work for the extension without disrupting. So we may be extending this loop off of the first unit. We haven't got a final design in for the few racks that we would be extending this CDU to support, but it will require at least a 1 day, probably a 2-day outage when we do it. So beware when you go down that path. Put in extra plumbing under the floor with extra connections and shut off valves.
So who did the actual installation of your plumbing? Was that somebody that your facilities contracted, or that Dell or Cool IT contracted?
Yeah, so everything beyond the CDU was done by a mechanical subcontractor that we worked through the building engineers to engage. The blue piping with the green couplers and port kits that you see, that's part of the Cool IT services that they perform during their install. They also connect up the rack manifolds and do the initial turn up, fill, bleed, and testing.
So did you feel that they were kind of ahead of the curve for teaching you some of these things that you're answering Alistair's nice question about planning for the future? Did they lead you to that, or did you have to kind of figure that out for yourself?
So I think we all came to it at a similar time. The Cool IT people might have had a better perspective on it. It's just that we never had that type of interaction. But the HPC architect, the Dell that we were working with, I should mention that this was the first warm water direct to the chip system that Dell installed here in the US. So I think that part of our challenges are probably because of just, it being early on in the product line, and experiences will be different today. They probably have it in their, internal knowledge now. This is what you want to do so that you have future expandability without too many headaches.
Thank you.
Any other comments or questions? So just a couple resources. There's a plethora out there. These are pretty good ones. And like I said, if you want to follow up with me directly, feel free.
Well, feel free to throw out questions while I'm talking if you have any, but we really appreciate your time, Doug, and your effort putting this together. That was really valuable. We had some good questions that have come out. Again, I'll make a plug to everybody else. If you have some ideas for topics, feel free to reach out to Troy and I, and we'll help work to get them into future, systems-facing track calls. And otherwise, we really appreciate, again, the presentation, Doug.
Great, thank you all.
Well, if there are no additional questions, we can go ahead and call this a complete meeting. Thanks, everybody.